Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at linear dependence and independence. So we're going to start with linear dependence, and I'm going to start with an example, but we're also going to quickly transition into a general concept, and here it is. Let's start with the matrix A, and we'll just start with a simple example, 2 columns. Maybe the first column, I'm going to call it A1, that's a column vector, and the second column is A2. Now, that would be a general matrix, but I think that's hard to see when we first start. So let's say that A1 is the vector 1, 2. And that A2 is the vector of 2, 4. Now, if you look at this, what have I done here? What I did is notice that if I took 2 and I multiplied it by A1, well, that's 2 times 1, 2. That is the vector 2, 4, but we just said that 2, 4, that is the vector of A2. Now here's what I'd like to try. I'd like to do this. Let's solve A times x equals 0. Now, we could do this with row reductions, but I think you miss the point that way. So let's write it this way. Remember what this means. This means that you have the matrix A that has columns A1 and A2. And it means you have scalars of x1 and x2. And the matrix equation, conceptually, is about linear combination. So let's do that. This is the linear combination of x1 times a1 plus x2 times a2. And that equals 0. Well, notice, but what did we already say? We just said that x1 times a1 plus, but we said that a2 is just twice a1. So this is x2 times 2 times the vector of a1. And this equals 0. Well, look at, I have a common factor of a1. So let's write this as x1 plus 2 times x2 times the vector of a1 equals 0. Well, we already know this. If a1 is the 0 vector, there's nothing interesting here. So we're going to say that what we already saw is that a1 is not the 0. I'm going to put a vector symbol over that for just pure clarity. So the a1 is not 0. What does that tell us? That means that x1 plus 2 times x2, this has to be 0. The scalar 0. Well, this says then that x1 equals minus 2x2. Well, okay, what does that mean? That means that x1 is dependent on x2. So we'd say x2 is free to vary. So for example, so let's do that. For example, we could have that if x2 is equal to 1, well, you could just put a 1 in there. You could see that x1 is equal to negative 2. Let's just see, does that equal 0? Well, if I write my linear combination, that's minus 2 times a1 plus 1, that's my x2, times 2 times a1. Well, clearly that's minus 2 a1s plus 2 a1s, that's 0. Well, hold on a minute. What this says then also is that this is really the problem of minus 2 x2s, that's what x1 is, plus x2 times 2 times a1 is equal to 0, and that is always true. So what we write then is my null solution here. My null solution says that x1 is minus 2 x2s, and x2 is x2 Well, that's just x2 is a scalar multiple. I can write it this way. So this is minus 2 times 1. So what this is telling me is this. We already said that if you have the vector negative 2, 1, so for example, if I made a quick little sketch. The vector of negative 2, 1 would be this vector, probably right about there. Well, what it's telling me is that any single point that lies on that line going this way, or any single point going this way, any multiple of that solves this equation. That's what it means to be dependent. So dependent vectors. Dependent vectors solve x1a1 plus x2a2 . So notice this. When I began this problem, I began the problem of trying to solve 1, 2, 2, 4 times some vector x is going to give me the 0 vector. And what did I find? Well, if I wrote this as the augmented matrix, 1, 2, 2, 4, 0, 0, and I perform a row operation of row 2 minus 2 row 1s, then I come up with 1, 2, 0, 0, 0, 0. I come up with this. Here's the key piece. The key takeaway is we end up, when we have dependent columns, we always end with a row of zeros. Okay, that's the big key, row of zeros. Okay, let's take it and see a little bit further. This time we'll use the matrix of A, but this time when we're talking about this has the vector v1, v2, v3, 4, v1, v2, v3. These are in R3. So each v has a v1, a v2, and a v3 in it. 3 components. So let's do this. Also, let's say these are dependent, and I'll come up with something a little bit more interesting. In a 2x2 case, dependence means that one column is a multiple of the other. When it's 3 or more vectors, that combination, you actually are talking about a combination of vectors. So it could be a simple multiple, or it could be a sum of vectors, or it could just be an actual full-on linear combination with with scalars and addition. Well, let's do a simple example. So suppose that v3 is really just the sum of the first 2 vectors, v1 plus v2. All right, solve ax equals 0. All right, let's try this. Well, it starts out the same way. We're going to write these as a linear combination. So x1, v1 plus x2 v2 plus x3 v3 has to give me 0. And then let's keep going. What do we know about v3? Well, we know that that is a sum of the first two. So x1 v1 plus x2 v2 plus x3 times v1 plus v2. And this has to give me the 0 vector. Well, how are we going to solve that? Yeah, carefully. That's how we're going to solve it, of course. Well, what does that tell me? If I regroup this, this says that I'm going to regroup this as, I'm going to regroup my v1s. So I'm going to write this as x1 plus x3 times v1 plus, and then I'm going to have an x2 plus an x3 times v2, and that has to give me a 0 vector. Well, how in the world would that happen? It's going to happen when x1 plus x3 is 0, and also when x2 plus x3 give me 0. Well, notice x3 is common, so let's solve for the dependent variables of x1, so that's minus x3, and x2 will do the same. That's just also minus x3. What does that tell me? It tells me this. It says that my null solution xn, which remember we originally said it's x1, x2, and x3. But what did we just find out? Well, we just found out that x1 is minus x3. And we found out that x2 is minus x3. And we found out that x3 is just a free variable. Well, whoa! x3 is now a scalar. This is minus, I'll write it this way, as x3 times minus 1, 1. Oh my gosh, look at that. What does this say? Minus 1, 1 times x3, that is a vector in R3 being multiplied by a scalar. And so what do I have? I have another set, an infinite number of solutions that would solve this problem. And that, again, is what happens when you have dependent variables. We said that not all the x's have to be 0. This is clearly the case. But I want to go backwards for a moment. Here's how I'm going to go backwards. Notice that this says that x1 equals minus x3. Or no, let's look at it this way. I'm going to grab my highlighter here. Let's take a look at each one of these equations. This one here and this one here. And I'm going to write those now in a matrix. This says that x1 plus x3 equals 0. So let's write it this way. x1 plus x3 equals 0. My next one says that x2 plus x3 equals 0. Well, if I was to write this as a matrix, notice that what I'm picking up is I'm picking up a 1, 0, 1, 0 in the first row. I'm picking up 0, 1, 1 in the second row. But wait a minute, there's no third row. But these are in R3. That means we don't write it if it's 0. So the third row had to be a row of zeros. Well, what is this? This is the augmented matrix. And it's really, this is the matrix of 1, 0, 0, 0, 1, 0, 1, 1, 0, times our vector of x equals the 0 vector. But notice what we have again when we have dependent columns. When we row reduce from A down to U or R, when we reduce to R, then what do we get? We have a row of zeros. We have a row of zeros. I'm going to put comma. I know that's probably, we'll call that stylistic English grammar. We have a row of zeros. I want everyone to be like, wow, what does that mean though? When columns are dependent, i.e. an infinite number of solutions. Infinite number of solutions to some matrix A times some vector x equals 0. We have dependent columns. So we didn't talk about independence yet. We're going to talk about it in our next video. But I hope that helps you to understand dependence. Hope that helps, and thanks for watching.